Today's lesson focuses on special cases in equilibrium. And in this case, we're going to talk about very small KEQ values. So sometimes we're going to do an equilibrium question, and we're going to notice that the KEQ constant is very small, and we mean really, really small. Usually it is around, 10 to the negative, 7 or 10 to the negative 8 and smaller. When you notice that you have a small K value, like this one, something should go off in your head and you should say to yourself, okay, that's a really small K value. There might be something here that I can do to make my life and my math life easier when I go to solve these questions. And the reason that you can do this is because if that K value is so small, we know that mostly reactants are going to be produced at equilibrium. So if mostly reactants are produced at equilibrium, then they're really not going to change in concentration very much. So if they do change in concentration, it's going to be a very, very small amount. And maybe it's so small that when you decrease the initial concentration by X, that it's often so small that that X term is not even going to impact that initial concentration, and you can actually neglect it. This is a good thing because it's going to make your math a lot simpler when you go to calculate your concentrations at equilibrium. So to know whether you can do this little trick, you have to do what we call a little test calculation. So what you do is you take your initial reactant concentration, and you have to have this, okay? So there's no other way to go around it. And then you divide it by the K value right here, and you'll get a value, okay? So we don't really care what the actual value is, but if your division of those two variables becomes greater than 500, you can neglect that change in concentration in the ice chart and then carry on and do some simpler math. So let's do an example where we have a smaller K value and get a sense for what we mean. So at 2000 degrees C, the KEQ is 6.40 times 10 to the negative 7. There you go. For the decomposition of carbon dioxide into carbon monoxide and oxygen. Calculate the concentration of carbon monoxide at equilibrium if 0.250 moles of CO2 is placed in a 1 liter closed container. Okay, so first thing that we need is we have to get our reaction written out. So stop the video, take a second, and come up with that balanced equation. So you should have come up with an equation of 2 CO2 is in equilibrium with 2 carbon monoxides and 2 moles of oxygen gas. This is a C. We're going to set up an ice chart because we know that these are these initial concentrations that they've added in. Now the volume is 1 liter, so that makes my molar concentration math quite nice. And we're going to fill in the ice chart as usual. So initially my CO2 concentration is 0.250 molar. Over on the product side, they're telling me that I don't have anything initially, so we assume that that's 0. Over time, that reactant concentration is going to decrease by X, so that at equilibrium, I'm going to end up with 0.250 minus 2X. Over on the product side, we're going to increase in concentration by 2X for carbon monoxide, X for oxygen. So at equilibrium, 0 plus 2X equals 2X. 0 plus X equals X. So we're suspicious, right, about this K value, and is it small enough? So let's do our check step next, because if we can neglect our change in X, we want to do that now before we start any algebra. So we're going to check for small k. And remember what we do. We just simply take the initial concentration, which is 0.250, and we divide by the K value, which is 6.4 times 10 to the negative 7. And again, all we care about is, is this division greater than or equal to 500? And it is. Okay, so double check it in your calculator. You're going to notice that it is. And then you're going to write for me, therefore we're going to neglect x. And I'm going to show you exactly what we mean, because we can't neglect all of the x terms, but we can neglect some of them. So we're going to set up our KEQ step, right? Number your steps in case you're all over the paper or the whiteboard like I am right now. We're going to take concentration of CO2, CO, is our product, squared times the concentration of oxygen divided by now the concentration of CO2 squared. We have our KEQ value of 6.40 times 10 to the negative 7. And then this is where we're going to stop, because we're going to be putting in these x terms from the ice chart. Now, what is it that we can neglect? We cannot neglect these, okay? You can't do that because that's all I've got. So if I neglect the concentration of those two products, that's telling me that I don't make any. And if I don't make any, then I don't have an equilibrium. So I can't neglect those. But remember what we're saying. We're saying that this K value is so small that this change in X right here is going to be also so small that when I subtract it off of my initial concentration, it really shouldn't impact that initial concentration. So that is the X term that we can neglect. So we're going to sub in everything else. So I have 2x squared times x divided by 0.250. And again, we're going to neglect that change in x squared. So we want to get our x terms grouped together. So just a reminder here, we're going to take this, I'm going to square that value, we'll cross multiply it. We're going to get a value of 4.0 times 10 to the negative 8. And then when I expand 2x squared, I get 4x squared times x is going to give me 4.0 times 10 to the negative 8 equaling 4x cubed. We're now going to solve for x, and I'm just going to come over here. So x is going to equal the cubed root of 4.0 times 10 to the negative 8 divided by 4, and we're going to get an x term of 0.0022 molar. So see how small that x term is. The idea is, again, if I took this x term and I came back over here and I subtracted it off of that initial concentration, it's really not going to change my 0.250 molar concentration at all. And this is why we can do this, but only if we check for small k and it falls under this category. So let's finish this off. Step 4, it asked for the concentration of carbon monoxide, and carbon monoxide is over here, it's 2x. So concentration of CO at equilibrium is equal to 2x. We know what x is from above, so we get a concentration of 0.0044 molar. And just keeping with significant figures, we should have that extra 0 on the end because we need the 3 sig figs from the initial concentrations there.